Welcome students. So today we will discuss about polynuclear hydrocarbons, and this is a part 1. It's a new unit. So let's move on to this interesting topic. So what is polynuclear aromatic hydrocarbons? So they are basically they are aromatic hydrocarbons, meaning they contain only carbon and hydrogens, and they are fused. These two aromatic groups are fused. For example, aromatic we can immediately think of benzene, right? It is the simplest aromatic compound available, and for example, if the two benzenes are fused, then it is become poly meaning is many. So it is having more than one aromatic groups in the in its structure. So and it only contains carbon and hydrogen atoms. So for example, here I have given three important examples of this polynuclear aromatic hydrocarbons. The first one is naphthalene. As I said, it is a fused a ring of two benzene rings, right? Two aromatic benzene rings. So this is a simpler example of polynuclear aromatic hydrocarbons. This is the basic one, because the one is not, if you are having one aromatic group, that is not considered as PAH, polynuclear aromatic hydrocarbon, PAH. It should contain at least minimum of 2. So it is having more than one aromatic groups, like in naphthalene. And the another example is anthracene. Anthracene is having 3 aromatic groups attached, fused, right? Fused meaning it is attached here in this section. It is attached, they are fused. So it is having 3 aromatic groups, 3 benzene rings. This is anthracene, and the same, it is also having a 3 aromatic rings, phenanthrene. But the only difference is anthracene is linear structure and phenanthrene is angular, means it is not linear. So I have already told that important examples include naphthalene, anthracene and phenanthrene. So naphthalene is a 2 ring system, 2 aromatic ring system, right? And anthracene is having a 3 aromatic ring system, and it is linear structure, linear shape. And the phenanthrene is a 3 ring system but angular shape, not linear one. So now let's move on to see the properties are some of the properties on how from where we can get this PAH, and what are these chemical or physical properties. So they are neutral. They meaning there is no charged species in this compound, right? If you see here, all this the polyaromatic hydrocarbons, they are not having any polar groups. There is no dipole in this compound, so they are neutral. They are non-polar. So neutral becomes automatically it's a non-polar atom molecules. So PAH are found in fossil fuel like coal and oil. So you will find this as a obtained as a byproduct, right? And they are also found in high levels in cooked foods. For example, if you cook meat at a very high temperature in open flame, right? T is temperature here. So you will also obtain. You can also obtain this polyaromatic hydrocarbons. And importantly, they are carcinogenic and mutagenic. So they are not good for the health, right? If you consume, it is not good. So these are the important properties of the polynuclear aromatic hydrocarbons. So what about the aromatic properties of polynuclear hydrocarbons? We all know that is this is aromatic, right? So we can verify, we can check whether this is a really aromatic compound or not, right? So how to check easily? We have already seen in the first unit in benzene chapter how to see whether a compound is aromatic or not aromatic, non-aromatic. So pH compound should be cyclic, right? pH compound should be cyclic, then only it comes under the aromatic property. So you can see here all the PAH compounds are cyclic, having a cyclic structure. Let's say this one, cyclic meaning it is not only a circle, right? It can be any ring shape. But the important point is we start from one point, and if you go, you should reach back the same point without any break. So let's see in the case of naphthalene, if you start from this point, you go here, you go without any break anywhere, you can also come back to the same point again. So it is a cyclic system, right? You can also go here, go here, go here, and go here, go here, go here, and come back here. So we can, without any break, we can come back in a cyclic manner, right? Like either this way, like in benzene, or in the case of like this way. Same thing here in the case of anthracene and phenanthrene. You can also, this is also a cyclic system. There is no break. You can go here and you can come back in the same position. Same thing here. So they are all cyclic system. So for compound should be aromatic, it should be a cyclic system, and this follow all this the cyclic rule. Planar, the PAHs are planar. So planar, all the compounds should be planar if it is aromatic. So if you see here, in the case of all the poly aromatic hydrocarbons, PAH, it is all planar. So it's a flat molecules, right? It is not bent like we see in the case of cyclohexane. That is not planar, right? It is a chair structure. It is having a chair structure, a boat structure. So, but this is in the case of polyaromatic hydrocarbons, they are all planar, they are flat molecules, they are fused together. So, it should be flat. If you see the three-dimensional structure, they are all flat molecules, right? So, they are planar. So, this also satisfies, their compound is cyclic, they are planar. What about the next point? It's having a delocalized compounds or contains delocalized double bonds. What is the meaning of that? Delocalized double bonds. Delocalized means it is having a alternate single and double bond, right? So if you see here, in the case of naphthalene, if you have a single double bond here, single bond here, 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 and you come back to the same point here. Here's a cyclic system. So it is having an alternate single and double bond, or it is called as delocalized double bond. It is not localized because it can also move. This double bond can go here, this double bond can go here, this becomes a double bond, this becomes a single bond. So there is a localization, right? Delocalization in the double bond. The compounds are having a delocalized double bond. This is the case of naphthalene. The same in the case of the anthracene. You see here double bond, single bond. If the double bond goes here, this double bond can migrate here, so it will change also. But the important point is you can easily see it is having an alternate single and double bond. So double bond here, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond, like that. Same thing in the case of phenanthrene. So these three properties of aromatic properties are satisfied with the PAH. The last one is it should follow the Huckel's rule, that is a 4n plus 2 rule, right? A compound, if it is if any compound should be aromatic, if it is follow this 4n plus 2 rule. We have seen this follow the three rules. Whether we can check also, we can easily verify whether it follows this Huckel's rule. Huckel is a scientist from Germany. So let's see how we can verify the Huckel's rule, whether the pH, these three examples I have given, we can follow this Huckel's rule or not. So Huckel's rule is 4n plus 2 rule. In this rule, the 4n, right, this n should be a positive integer. If it is an aromatic compound like 0, 1, 2, 3, etc., it should be a positive integer. Then it is called as aromatic hydrocarbons, aromatic compounds. Yeah? But if when we solve this using this equation, and if we get a negative value of any of n or fractions, then it is non-aromatic, or then it is called not aromatic compound. That is not an aromatic compound. It should contain n value should be a positive integer. So let's see how we can calculate the 4n plus 2 rule, Huckel's rule, for this naphthalene, anthracene, and phenanthrene. You can see here, let's take the example of naphthalene first. Naphthalene contains 10 pi electrons. How do you know that? It contains 5 double bonds, 1, 2, 3, 4, 5. It contains 5 double bonds, meaning each double bond is having 2 electrons. Right? Each double bond is made of 2 electrons. So 5 double bonds meaning 10 pi electrons. So naphthalene contains 10 pi electrons. In the case of anthracene and phenanthrene, it contains 14 pi electrons. Why? How many double bonds that it's having? Count it. 1, 2, 3, 4, 5, 6, 7 pi bonds. Each pi bond donates is having 2 pi electrons. So total is 17 pi electrons. 7 into 2. So let's take the example of naphthalene first and check whether we can solve for the 4n plus 2 rule. So 4n plus 2 rule is meaning it should contain 4n plus 2 pi electrons, or 4n plus 2 equal to pi electrons. So this is the first equation we can write, and then we can solve for the pi electrons. So 4n plus 2 equal to 10 pi electrons in the case of naphthalene. This is naphthalene, 10 pi electrons. So what is the n value? The 2 will go here, and then 4 will come to the denominator, right? So n will be 2, right? 10 minus 2 is 8. 8 divided by 4 is 2. So n is 2. So n is 2, meaning n is comes under this this first in the first one, that is n is equal to 0, 1, 2, or like positive integer, right? N is a positive integer. So this naphthalene is an aromatic compound. So we found out that naphthalene is satisfy all these 4 rules and is aromatic compound. What about this anthracene and phenanthrene? Same thing. Anthracene and phenanthrene contain 14 pi electrons. So 4n plus 2 is equal to 14 pi electron. So n value we can easily calculate. 14 minus 2 is 12. 12 divided by 4 is 3. So n is 3. And again n is a positive integer and this comes under this one. N is 0, 1, 2, 3, etc. This positive integer. N is 3 is a positive integer. So this is also satisfy the Huckel's rule, and also it satisfy all this PAH, satisfy all this 4 rules to be aromatic compound. So these are all aromatic compounds. We can verify easily by these 4 rules, and importantly using this Huckel's formula. So now let's move on to see the classification of polynuclear hydrocarbons. How it is classified, right? So polynuclear hydrocarbons are classified mainly into 2 types of structure, whether it contains a benzene ring or it does not contain a benzene ring, right? So these are called, if a polynuclear hydrocarbon is having a benzene ring, aromatic compound, if the structure is having a benzene ring, it is called a benzenoid compounds or benzenoid polynuclear hydrocarbons, right? So this is the first classification. Or non-benzenoid ring. Non-benzenoid ring, it is not having a 6-membered ring, right? Benzene is a 6-membered ring, and non-benzenoid maybe a 5-membered ring or 6 or a 7-membered ring. You can see here this structure, it is a 7-membered ring here. This is 7 1, 1 or 8 1. 1 you can count it 1 2 3 4 5 6 7, right? This is a 7-membered ring, and this is a 5-membered ring 1 2 3 4 and 5. So this is 5 and this is 7, right? So this is a non-benzenoid compound, but it is a polynuclear hydrocarbon because it is having a flat structure and it is a fused one. It is having more than one aromatic ring. So this both are aromatic. You can see here there is a 10 pi electrons, right? 5 double bonds like benzene, like naphthalene. So it is a aromatic compound. So this is the first classification. Polynuclear hydrocarbons are classified mainly into 2 types: benzenoid compound and non-benzenoid. Benzenoid having a benzene ring type in the structure, and non-benzenoid compounds having a non-benzene ring structure like 7-membered ring or 5-membered ring. So this benzenoid is further classified into 2 types, whether it is an isolated polynuclear hydrocarbon, right, or fused one. So now let's see the example of an isolated one, how it looks like. Isolated one meaning it is having a it's having more than one aromatic compound, right? Aromatic groups, like this is a benzene ring, is an aromatic group, and this is a benzene ring, is an aromatic group. There are 2, so it is a poly, right? More than one, but it is not fused, right? So it is isolated, meaning it is isolated. The 2 groups are not fused; it is isolated. This is a diphenyl. This is a diphenyl, and is also, they can also look at triphenyl, a diphenyl, methane. All are comes under the isolated benzenoid polynuclear hydrocarbon, right? Isolated benzenoid polynuclear hydrocarbon. These are comes under this category. So what about the fused one? We have already seen the fused one, right? We have already seen it. This is also having a 2 types, whether it is a linear one or angular one. Angular one is anthracene. We have already seen the structure anthracene. There are 3 benzene rings and they are in angular structure, and the linear one is like this, the naphthalene one. So, what are the example? What is the linear fused benzenoid polynuclear hydrocarbon is naphthalene, and example of angular fused benzenoid polynuclear hydrocarbon is anthracene. So, this is how the polynuclear hydrocarbons are mainly classified, mainly into 2 types, that is benzenoid and non-benzenoid. And under benzenoid we have isolated one and we have a fused one, and the fused one we have linear and then angular. So, it is easy to remember if you go in this way, right? Angular fused benzenoid polynuclear hydrocarbon is this one, linear fused benzenoid hydrocarbon is this one, like that. Isolated benzenoid polynuclear hydrocarbon is this one. So, we can easily remember using this the easily the visible this chart structure. So, with this we will move on to see how the polynuclear hydrocarbons are nomenclature, how they are named, or how they are assigned the ring structure and all. So, polynuclear hydrocarbons up to 6 fused rings. Okay, if you have more than if you have up to 6 rings, right, it is called as small PAH, or is considered as a small polynuclear hydrocarbons. And if it is more than 6 fused rings, it's okay. If a structure contains, let us say 7 or 10 fused rings, it is considered as a large PAH. So, this is how we differentiate between the small PAH and large PAH. Less than 6 or less than 6 is considered as a small PAH, and more than 6 fused rings, if it contains, it is considered as a designated as a large PAH. So, now let us see how to number the ring. Okay, because in benzene we can number easily because it is having only one aromatic group. But in the case of let us say naphthalene, it is having a 2 fused rings, right. So, it is we have a special nomenclature system, numbering system or numbering scheme for this polynuclear hydrocarbon. Let us say this one. So, given the structure of naphthalene, and in the case of naphthalene you can see that the number starts from here, right. 1 is this carbon, and the second carbon is here, third one, fourth one, and fifth one is goes to the next group, next aromatic group, or in the case the next benzene ring, 5, 6, 7, 8. Okay, and this fused area, you can see here, this is a fused area, is designated as 8A. So, 8 after 8, 8A, or this after 4, it is 4A. So, this is one way to number the polynuclear hydrocarbons. Another way, or we can also use this another way as shown here, right. We can also number the naphthalene ring by in this way also. So, same thing, it is starts from here 1, 2, 3, 4, 5, 6, 7, 8. Instead of 8A, you can also number as 9 here, and instead of 4A, you can also number as 10. So, basically it is coming like a cycle. So, it goes from 1 and then stop here 8 and then goes 9 and 10, right. So, it is coming again a cyclic scheme. So, either you can use this numbering scheme is also fine, and also this numbering scheme is also fine. So, this is how you number the polynuclear hydrocarbon. So, now let us move on to see the method of preparation of polynuclear hydrocarbon. So, in the first case, as you can see in the classification, we have classified benzenoid compound. It is 2 types, isolated one and fused one, right. So, we can see first how to prepare the isolated PAH, right, diphenyl, or this one, this is a diphenyl methane, right. It is attached, there is a central carbon attached here between the 2 phenyl ring, 2 benzene ring. So, how this we can prepare this diphenyl methane. So, what is diphenyl methane? So, diphenyl methane is an isolated polyaromatic hydrocarbon, right, because it is the 2 benzene ring or 2 aromatic groups are not fused, they are isolated, but it contain in the same in the one molecule, both are contained in the one molecule, right. So, that is isolated polyaromatic hydrocarbon. This can be prepared by treating this benzyl chloride. So, this is benzene ring and having a CH2Cl, benzyl chloride plus benzene, and in the presence of AlCl3, that is a Friedel-Crafts reaction. So, we have seen in the unit 1 that AlCl3 and this reaction is called as Friedel-Crafts reaction, right? Condensation reaction, this one. These two will react and to give the diphenyl methane. So, the chloride will go away and this will attach to this benzene ring, right? The chloride will go as an HCl, hydrochloric acid. So, one hydrogen is gone from here and one HCl and one chlorine to give the HCl also. So, this is how we prepare the diphenyl methane. This is the first method by the Friedel-Crafts condensation reaction, right, by treating benzyl chloride with benzene in the presence of, this is very important, AlCl3 as an Lewis acid catalyst. So, in the second method, we can also use this method like benzophenone reaction. So, if we take benzophenone and use this reduction reaction, that is using hydrogen and nitrogen, nickel. So, nickel as a catalyst, hydrogen as a gas, it is used for reduction. So, this reduction is loss of oxygen or addition of hydrogen, right. So, benzophenone is having a oxygen in the center, double bond O, this carbonyl group, and if you add this catalyst within the presence of hydrogen gas, you will get hydrogen will incorporated and oxygen will remove. So, this is the diphenyl methane. This is how we can also make the addition of hydrogen here and loss of carbon oxygen in the product. So, this is a reduction reaction. So, this diphenyl methane can also be prepared by or synthesized by treating benzophenone with nickel hydrogen reduction reaction. So, I have given two important reactions methods to prepare this isolated PAH. That is, example isolated PAH is diphenyl methane. Now, let us see some of the properties, that is the chemical reactions of isolated PAH. So, diphenyl methane as an example we can see. So, diphenyl methane undergoes several reactions like nitration, bromination, and in this lecture we will see these two important reactions, that is nitration and the halogenation reaction. Halogenation meaning chlorination, bromination, right, iodination, etc. But in this for this we will see one example, that is bromination reaction. So, first we will see nitration reaction. So, nitration reaction we already know, we needed concentrated nitric acid. So, if you take the diphenyl methane plus concentrated nitric acid in the presence of sulfuric acid as a catalyst, right, what will happen? We will get a nitro substituted diphenyl methane, like diphenyl methane, and this one is nitro group attached here, or we can also say this is a mono nitrophenyl methane because it is having a one nitro group or one nitrophenyl methane. So, if we further add more nitric acid, you will get dinitrophenyl methane as shown here, the structure. So, two nitro group attached, one here and one here. So, this is the reaction of diphenyl methane with nitric acid and sulfuric acid, that is called the nitration reaction. Second reaction will be the arangylation reaction, you can see. In this case, we will see a bromination reaction. This is also a simple reaction. You take this diphenyl methane and add the bromine in the presence of light, some UV light, H mu. What you will get is the diphenyl methyl bromide. So, the bromine will go here and attack here because this is a very reactive area for the bromine. So, first it will go here only. So, it will go and form this monobromo. So, diphenyl methyl bromide or monobromo diphenyl methane, right, monobromo diphenyl methane. So, this is the two important reactions of the isolated PAH, that is the diphenyl methane. So far we have seen the importance about polynuclear aromatic hydrocarbons, right, why it is called as aromatic. We can also confirm by these four important rules of aromaticity. And we have also seen that important structures of and with some with 3 examples of polynuclear hydrocarbons, and also the classification, important classifications of polynuclear hydrocarbon, and methods and preparations, preparation methods, and important chemical reactivity of this isolated PAH, and we have took that diphenyl methane as the example. So, this so far we have seen all these things, and this class we will see more interesting polynuclear hydrocarbons like naphthalene and other anthracene, phenanthracene in the next class. So, this is all for this class, and I will see you in the next class. Thank you.